Good morning or good evening, depending upon where you're joining us from today. My name is Carol Urbano, and welcome to this edition of the MIT Chat. I'm your host today from the MIT Museum, and I'm going to introduce us to our featured speaker today. Fatima Hussein, our very own curiosity correspondent. She might look very familiar to many of you who have seen the Home Labs videos or some of the challenge videos. In addition to her role as a curiosity correspondent, Fatima is a geobiology and astrobiology researcher in the Summons Lab here at MIT, and today she's going to talk with us about exploring Earth and other planets for ancient life. So welcome, Fatima.
Thank you so much, Carol, for the kind introduction. I'm really excited to speak with you all today about my background and the stuff that I do outside of making videos as a curiosity correspondent here at MIT. So when I'm not making videos in the lab, I am on a quest to explore ancient Earth and what it was like and other planets for life, which I think are some really, really exciting questions. So let's dig in. So to begin, I wanted to give you a little context about who I am and how this background even started, because I want to show you that there is no one-size-fits-all approach to doing this type of interdisciplinary study. So I started out as a kid who was so interested in gardening and plants. So that's a picture of me in a flowery field in Houston, Texas, which is where I was born, to two parents who immigrated here to the US from Pakistan. So I was interested in gardening and flowers and the natural world. And my parents were kind enough to give me a little itty bitty gardening plot when I was really little. And I used to toss all sorts of seeds and bulbs in there, not reading the instructions, not following the book by any means, and just seeing what popped up and grew. And soon I became really, really curious about the mechanics and the science behind all of it. So that led me to Brown University, which is a medium-sized college just a little bit outside of Massachusetts and in the smallest state in the United States, Rhode Island. So in Rhode Island, I went to Brown University and I had the chance to study something called geochemistry. So that's the chemistry of the earth and the natural world. So that was within the geology department. So people study rocks and the inside of the planet and other planets and all that amazing stuff in that department. And I was just focused on the chemistry part of it. And I had the opportunity when I was a sophomore to join a lab and do some hands-on research. So remember, I used to be digging my hands in the dirt, you know, getting totally immersed in science as a little kid, looking at bugs, looking at the creepy crawlies, looking at flowers. So I finally had this opportunity to get into the lab and do science and do it in a controlled environment where we were reading the instructions, where we were following the book, and we were trying to answer some really important questions about how the climate has changed over time. So if we look outside today in Cambridge, Massachusetts, which is where I'm located right now, right outside of MIT, it's cloudy out. I'm looking out the window and it's totally cloudy. So the weather is the conditions we're experiencing right now, but the climate is these long-term weather trends. But humans have only been around for a really small part of Earth's history. So we don't have written records about how climate changed over the past, thousands of years behind us. So part of what we do with the chemistry is we're looking for little molecules or little signals that might be able to tell us how climate's changed over time. So that's the kind of research I got to do at Brown. And I specifically focused on a mountainous region in Alaska, which is super far north of us. And I got to study how it changed over the past 12,000 years. So that was really, really exciting. Getting into that kind of research really fully immersed me in geology. Before I actually started studying geology, I initially started out as a pre-med student. I thought, okay, I'm good at science. I love tweaking with things. I love getting my hands dirty. I like a bunch of different circumstances in each situation. I like a lot of moving parts. So I was like, obviously I should be a doctor. And my parents were totally gung-ho about it and really supportive. So I started out in pre-med, but then eventually realized there's another way I can study all of that. And that was geochemistry. So after joining that lab and getting the opportunity to do that amazing research where you're studying the chemistry of life and the chemistry of the natural world, I started to realize that there were some really cool questions we could begin to answer using this kind of interdisciplinary study. So remember, I'm studying geochemistry, and that's a amalgamation of two words, geology and chemistry. So you're super, super interdisciplinary in that. And you can start to look at the natural environment. So you can see in the picture in the middle of the screen, there's a little person looking up at these gigantic features around her. That's me in Iceland looking at basalt columns, which form in really unique environments. And I got to figure out, oh, there's a lot of cool chemistry and a lot of cool stories behind how that happens. And that led me to ask some bigger questions about Earth. So how did the Earth change over time? What enabled us to get to where we are today? And you can start to actually ask within the realm of geochemistry and geobiology and all these other cool related fields, you can start to ask the same questions of other planets like Mars, which is in the top right corner of my screen. So I got so excited about this information that I was learning and synthesizing, and it just was an explosion of wonder really for me. And it was like the coolest time of my life, just asking questions left and right and figuring out that if we combine a lot of different fields and combine a lot of disciplines, we actually have a chance at answering those. So I loved talking about it and loved telling my parents all about it and my grandparents and my family in Pakistan and all my friends in college and my friends from high school and everyone. But I was noticing that they weren't really getting it. So I took a brief foray right after I graduated from my undergraduate school, Brown, to come to MIT and to actually study communicating that science. So when I came here, I was really initially intending to learn how to communicate about earth science, but I learned how to chat with different folks about all sorts of other sciences and write about them. But at the end of the day, I was still definitely interested in earth science. And when I got to MIT on my first day for orientation, and I get to go to the science writing lab where I was going to spend the next few months of my life, I got to my locker and it had my name and it had a couple stickers on it. And one of the stickers was a NASA sticker. And I think that that was really a foreshadowing of the kind of work I was going to do after grad school. And again, I didn't put that there. They were already there. So I really think that there was a lot of fate and kismet involved in kind of pushing me towards my future research and the kind of work I do now. So right after graduating, I had the opportunity to join the Summons Lab, which studies geo and astrobiology. And you can see me on the far left and my amazing colleagues in this entire photo. But in the middle, there's a fantastic smiling man, and we're all surrounding him. And that's Professor Roger Summons. And he's my biggest science inspiration. He's been studying geo and astrobiology for nearly his entire career and is really one of the leading people in the field. So it's absolutely so exciting to be a part of this lab and to think through questions with him and work with my amazing, amazing colleagues every single day. It's super, super exciting. So I want to talk a little bit about what geo and astrobiology really is. So I told you I started out in this field called geochemistry, but now I'm talking about biology, like what's changed here, what's different. So geobiology is the study of life on Earth. So it's the study of ancient life, life now, anything that's alive, really. And it's just studying it in Earth. So this isn't, this is stuff in natural environments. And you may have heard in your science classes about microbes or extremophiles, which are microbes that like to live in really extreme environments, like where it could be really, really, really hot or really, really, really acidic. Those are the kinds of microbes that you can study in geobiology as well. But it's really a study of like all the living things on Earth. And it's really fantastic. And it is really, really well tied to biology. Astrobiology, on the other hand, is the study of life on other planets, and like Mars, which I've included again. But as far as we know right now, Earth is the only planet in the universe that has life on it. And in order to better understand how life could have arisen on other planets, we really have to look introspectively. We have to look at ourselves. How did life actually come to be on our own planet? How did our planet change over time? Why do we have life on Earth, whereas we're not seeing life on Mars today? So as you can see, between geobiology and astrobiology, I have this gray arrow that's pointing in both directions. I want to make the point that a lot of these studies feed into each other. So in geobiology, we can gain a better picture of how Earth really evolved by studying other planets like Mars. So what makes Earth unique? The best way to look at that is to see what makes it different from other planets and to study those other planets to help tell that story. And for astrobiology, if you're looking for life, why not look for life from the perspective or from the knowledge that we gain from studying the only planet in our universe that has life, which is our Earth. So these really feed into each other. So it's a constant back and forth between these two fields, and they really inform each other, and they're both very exciting. So that's why they're really closely tied together in our lab and a lot of different labs around the country and world as well. So what I study in particular is ancient life. And I would say that this is the case for my colleagues as well. We're always seeking out ancient life. So what does ancient life really mean? So you and I might initially think of fossils. So on the left is a picture of me deep in the background of the American Museum of Natural History in New York, where scientists actually study these fossils. So this isn't the stuff you're going to see on display. This is the back end of all of that. This is all the behind the scenes. So a colleague of mine who's doing a PhD at the American Museum of Natural History in paleontology, studying those big fossils and how life evolved from there, he let me see some big fossils, and they were bigger than me, and I was ecstatic to actually get to hold something that big. But in our lab, we're not studying those kinds of fossils necessarily, even though some people have studied things related to dinosaurs. What I study in particular is life that you and I probably wouldn't be able to see with our own eyes. It's life that we would have to look at under the microscope. But if we're looking at ancient life, that means that life isn't alive anymore. It's not there. So we can't just look under a microscope and figure out what life was like and how it's changed over time. What we can look for is evidence of that ancient life. So things that maybe those microbes could have left behind. Things like little tiny molecules that have different structures based on their environment, or different structures based on the climates in which those microbes lived. So we look at these things in rocks. So on the right-hand side, I have rocks that I actually study that contain millions of these millions or even actually billions of these molecules that we can study to find out clues about ancient environments. So it's been really cool to be kind of sleuthing around ancient Earth. Now I have a question for you all, and I'd like to see where we're all at and to give you a look into what ancient life could possibly mean. So I'm going to have a poll, and I want to know what you guys think. How old are these rocks? How old are the rocks that I've been studying at MIT? I see some really good votes coming in. That's awesome.
Doesn't look like anybody fell for your 70 years, Fatima.
Well, honestly, I'm glad to hear it. I hope we didn't just dissuade someone from voting that way. They're like, oops, I shouldn't vote that way now. It looks like we have a good number of votes in. So it looks like people are guessing mostly between 170,000 years all the way to 107 million years. But the winning vote, it looks like it is 1.7 million years. So let's see if you guys are right. All right, okay, poll is ended, fantastic. All right, so I wanted to give you an idea of what these ages really are, but you guys seem to be ahead of the curve and guess the right answer off the bat. But 70 years is like the age of my grandma. I'm not studying things that are 70 years old. I'm hanging out with them, actually. So that's my beautiful grandma in Pakistan, where she lives. So she's 70. If we look at 170,000 years and what's going on 170,000 years ago, that's when some historians think that humans started wearing clothes. So those pictures that you're seeing are illustrations of what people were wearing just thousands of years ago, but that's when we think people started wearing clothes. So we're not studying that far with these. We're not studying that, that part of history with these rocks. What we're studying is 1.7 million years old. So you can see this really cool reconstruction of Homo erectus, which is one of our early hominin ancestors. And we're trying to figure out what the environment was like for these evolutionary cousins of ours. And for 107 million years old, which you can absolutely study with rocks. And I've had the privilege of studying rocks that are hundreds of millions of years old. 107 million years ago, horned dinosaurs came to America. So I just wanted to give you a little snapshot of what we consider recent time in geology. But of course, as I mentioned, we're focusing on 1.7 million years old. So we have these ancestors on Earth, but we don't really know what they lived like. What were their environments? We don't have written records of what happened then. So we can use tools like geochemistry and like geobiology to figure out what these environments were like and how they changed over time. And this brings me to the point that what we study in geobiology and geochemistry, the questions that we're asking in geology are ultimately how we came to be and who we are. Even though we're studying the Earth, a lot of what we study leads us to questions about ourselves. So that's why I think it's also really, really exciting to have the opportunity to study the environments in which our early human ancestors lived. So this is Homo erectus. Once again, we're trying to figure out what was this landscape that Homo erectus lived in? What did it look like 1.7 million years ago? What were the environmental conditions that might have driven its evolution? What, was there water around? Were these folks, how were they eating? What were they eating? What was the climate like? What was the weather like? We're asking all sorts of big questions. And every time we answer one of these questions, we learn a little more about ourselves, which is really, really exciting. We use a lot of different complicated methods to do this. So even though we're asking questions that might seem simple off the bat, like who we are and how we came to be, and they just say, oh, it's so easy to ask, but in reality, they're incredibly difficult to answer. We use a ton of different methods in this lab, and these are just some of the pictures I've had the opportunity to take over the past 2 years while I'm doing work in the lab. So we use some really advanced instrumentation that requires a lot of chemistry knowledge to get, and we are analyzing microbes and their different components and the organic molecules that make them up. And we use those to tell stories about how the Earth changed over time. And I think that's really, really exciting. And we have a fantastic lab to do it with and fantastic colleagues that we're learning from. So none of this work that you see in these pictures could be done in isolation. I single-handedly cannot answer any of these questions, and neither can my colleagues. We all have to work together with each other in our lab and in our greater community. So that's why we travel around the world to go to conferences, to present our work, to have those critical conversations with other folks. And that's how we continue to learn and how we can get closer and closer to these answers. So I mentioned astrobiology. It's in the title of my talk that we're looking for ancient life on Earth and on other planets. So we want to ask questions about these other planets, and we really need to find answers for them through the things we can study. So we have our best friend, the red planet, Mars, here again, which is my favorite planet to study and to talk about when it comes to astrobiology, and one of our lab's favorite planets for sure. And we're trying to see, what was it like billions of years ago on Mars? And Mars is about 4.5 billion years old. And our Earth is also about 4.5 billion years old. So we have similar ages, relatively similar sizes. Mars is a bit smaller. And we want to see, if our planets formed at the same time, how did the outcomes get so different? Why does Mars look the way it does today, whereas we're this lush green place with humans every single place on Earth? How did Mars change over time, and why? What led it to be so different? So the way we can study this right now is by astrobiology and really figuring out the theories behind this stuff. So I mentioned in my preview page for the talk that included the link to this, that I've traveled around the world in the quest to gain the knowledge necessary to begin to answer these questions. So a couple summers ago, I had the opportunity through NASA astrobiology to go to Santander, Spain, and study astrobiology with scientists from all over the European Union, scientists and students. And we got to have lectures in other languages and learn about how astrobiology could be studied around the world and what resources and skills people are bringing to the table, which was really, really exciting. I also had the opportunity to go to a JPL, so NASA's Jet Propulsion Laboratory, a workshop that they were holding about where to land the next Mars rover that's actually going to take off from Earth this year, about next month. So we're going to have a rover take off, and it was really, really cool to have a chance to apply the science I've been learning here at MIT and that I learned in my undergrad to help make decisions and to help learn about how we can best use what we know to go to the best place on Mars. So that was a very exciting experience. So as I mentioned, we have on July 20th, just pretty close to now, less than a month away, we have a mission rover taking off from the Earth, the Perseverance rover, and its aim is to study Mars and its environment and how Mars changed over time. And also it has a side mission to help prepare Mars for potential human explorations. So if you've heard of MOXIE, it's an instrument that's going to turn carbon dioxide into oxygen that could be used to not only breathe for humans, but also as fuel to help power what it would take to really live on Mars. So that's going to land in a few months after takeoff, and we're going to get a lot of knowledge out of it. So I'm really, really excited. Right now, on the other hand, you may have heard of Curiosity. So that's a rover that is just driving around Gale Crater on Mars and looking for evidence of ancient life and studying what's going on Mars today. And we have a lot of folks here at MIT, at Brown University, really around the country, who have a hand in Curiosity and how it's run and how it does its experiments. So one thing that's really exciting about Curiosity is it's been running for way longer than it was intended to. So it's still working hard, it's still doing a great job, it's still helping us learn about Mars every day. But when we send a rover off the planet, that's usually it. It's not coming back. We don't get to come home and look at Mars samples very often. And that's something that's really exciting about the Mars 2020 mission and the Perseverance rover. It's actually going to be taking little samples from Mars. So it's going to take little pieces of Mars, and hopefully we'll find a way to return those little pieces to Earth so that maybe one day you and I can actually study these samples in the lab and be a part of that bigger story about how Mars became what it is today. So the Mars 2020 Perseverance rover is going to land in this site called Jezero Crater. And Jezero Crater is the site of a multi-billion-year-old delta, which is an environment where there's usually a lot of water, a lot of waterways meet. So we think that this place was perhaps once wet. And we know from our studies of different deltas and places on Earth that deltas support a lot of life. They're teeming with life on Earth. So if we wanted to take a best guess as to where we would find evidence of past life, we would look at a delta on Mars, and that's Jezero. So I'm really excited to see what comes out of that. And I dream of being in a lab or being in a situation where if we are able to get samples back from Mars, that I will get to see Mars dirt and help tell that story about Mars's evolution. So in the meantime, again, because I went to graduate school here at MIT on how to actually write about and communicate science, I've had the opportunity to explore Mars so far by writing articles and by meeting people who have had the opportunity to study Mars and interviewing them. And it's been super fun. I've gotten to know a lot of people. One of my colleagues, Angel Maharo, has been doing some incredible research about Mars and how we could possibly detect life on Mars if we were able to get certain instrumentation up there, and what things we could look for and whether it's possible. So I think there's some really exciting work going on here at MIT, and I'm just so blessed to be a part of it and can't wait to see what happens in the future. One of the things that I also get to do here at MIT, and I'm also just encouraging everyone if they want to come to MIT to really give it a shot, reach for the stars. One of the classes I get to teach is on the origins of life. So we're asking these questions about how we came to be, We're asking questions of how did life originate in the universe, and what conditions made that possible. So that's also within the study of geobiology and astrobiology. So when you're thinking of these big questions in your biology class, like, how did this all really begin? You're starting to ask a lot of the same questions that we get to ask in the lab every single day. And this is all to say that this is a part of a bigger effort to tell the story of life. So here in this figure from a 1990 paper by the incredible scientist Carl Woese, describing the universal phylogenetic tree. So think of this as the tree of life based off of the information we know from genetics. So the things that encode who we are. In that little tiny, pinkish circle, number 15, that's us. So look at how much other diverse life is out there. Think about how this could have happened. Think about how we are such a small part of this huge, long story. And think about how you can leverage the tools you're learning in school to start to answer these questions, just like we are in the lab. And maybe one day you'll be our colleagues and we'll get to work side by side and ask these really interesting questions and work to answer them together. So I just wanted to end my talk by saying I'm really excited about the future of my field, but also the future of what you all are going to do. So as you all learn science in school and think, okay, this isn't going anywhere, this isn't my jam, think about these big questions that you could be asking. See if they can motivate you and help you get that motivation to study for that test and think, okay, if I study this and get a greater understanding of this, then I get to ask these really big, important questions that help inform our entire species and our history in the past and what we're going to be doing in the future. So with that, I wanted to encourage you all, if you want to see more and follow our research, on Instagram, you can follow our hashtag Summons Lab. A lot of our colleagues post really cool snapshots of their work, and that's a little lens into the lab. And I post about this stuff on my Instagram as well. So please follow, and I'm really excited to hear all your questions and speak with you all.
Thanks, Fatima. And as as you can see here, we're using the Q&A pod, so you can enter your questions there, and we'll take those. Well, you can also excuse me, upvote someone else's questions. I see some of you are already starting to do that. So Fatima, I'm going to have you stop sharing your screen for now, and then we're going to, while you're entering your questions into the Q&A pod, I'm going to take some from our students that were already posed on Global Campus. Yeah. So, so we have someone who is interested in, based on your studies, what do you think is more ancient, plant or animal?
Oh, that's a fantastic question. And so let's quickly try to think back to that tree of life I showed us. And if you don't have photographic memory, which I don't, let's think about the very end of that tree. So let's say this is the end of the tree, and these are my two fingers, and this is number 15, and this is like animals and plants, and there's one more, a fungi. As you can see, they're all originating at the same point at the same time. So it's actually pretty complicated to give a distinctive answer, but if you consider algae plants, which I do and folks do in my lab, then we can definitively say that plants came first. And that animals and fungi and these really advanced forms of life came later. So it's a really good question.
Nice. So we are also interested in, are there any specific discoveries that you've made or that the Summons Lab has made since you've been affiliated with it?
So I'll answer that in two parts. First of all, I have not made any major scientific discoveries yet in my life, since I am very early in my scientific career, but I still have hope. So check back in 50 years and we can talk then.
We have faith.
Thank you, Carol. I appreciate it. But one thing that I have discovered is that you can come into this field with anything. So if you love math or you love storytelling or you love science, there's a place for you in these studies. So now to the second part, which is things that the Summons Lab has discovered. We've been on the look for patterns in nature that tell us hints about climate. So we've been a part of discovering a lot of these patterns and writing about them in journals. So if we're looking for ancient algae, what should we be looking for? If we're looking for these kinds of microbes, what conditions should we be looking for? Our lab specifically has a focus on the evolution of complex life. And I can, in the guide before my talk, there's a link to our website. You can find out about the stuff we do there. But thankfully, we have made discoveries that help us piece together this picture about how complex life came to be.
Mm-hmm. Great. And I'm sure that other scientists are using some of that pattern discovery to do their own exploration.
Exactly. That's the way to do it.
Yeah, great. So we are also interested in if you have a favorite type of rock, either on Earth or Mars or anywhere else.
A favorite type of rock? That's a really good question. So I'll counter with this. I have a lot of favorite minerals, which are the things that make rocks. So I generally like the things that are shiny and glittery. So I like micas and I like labradorite, or things that really just catch my eye. So then I love seeing granites or these rocks that have a lot of these different minerals in them. So if you have a granite countertop at home or in school, or ever get a chance to see one, get really close to it. Take a look, take a magnifying glass, look at the different things you see. You're going to see a lot of cool stuff in there.
Great. And do you think life once existed on Mars? And do you think there's life there today?
I don't think there's life there today on Mars, because Mars, as far as I'm aware, and there are going to be scientists who might think differently than me, but I personally think that the environment on Mars that we have today is pretty uninhabitable. So it's pretty inhospitable to life, and it's being bombarded by a ton of radiation. So I don't really think there's life today, but I want to say that it would be super duper cool if there was life on Mars. And we can't really approach science with like an end in mind, being like, I'm setting out to prove that there isn't life on Mars, or I'm setting out to prove that there is. We have to be pretty agnostic about it. But I would like to believe that if we find life, it's going to be in those environments where we know that there's where we know there's a lot of life on Earth. So I know that if we're going to find life, it's going to hopefully be really informed by what we study here. Not a big answer, but it would be cool if there was life for sure. Like I would like scream for sure.
So I'm wondering what you think about the theory that there could be multiple universes.
That's a good question. Personally, I think that it requires some knowledge of philosophy and astronomy, and I can't really wrap my head around how it works. So I like to just focus on our universe and what we know. But I think it would be pretty cool. I mean, in science fiction, I see these things about multiple universes and multiple timelines. And I think that's really, really exciting, but I don't really quite understand how we can study it. So if you think of ideas, hit me up.
In the meantime, you'll keep it close to home in this universe.
Close to home in this ever-expanding universe.
Yeah. Sounds like a good strategy.
Yeah.
So we are also interested in understanding what planet or moon you think has the best contender for having life, either in the past or most hospitable for, I'm assuming, human life in the future.
Human life. Okay, so
I'm not sure. Whoever asked the question can clarify if they'd like.
I mean, they could ask about like tardigrades. So we know that there were tardigrades on the moon at some point due to a mission that went a little awry. But I mean, the obvious answer is Earth, even though I know that's not what you're asking, but Earth is the planet that's going to have life in the future and best supports it. But okay, outside of our planet, which is what you were asking. I think that Mars could be a really good place. We're looking at Mars for potential human exploration. We've been to the moon, but I don't know if we're going to have like a moon base or something. But being able to get boots on Mars in the future would totally change the game as to how we do science. So I think that if this Mars 2020 mission goes well and everything goes to plan, which we can never guarantee, we'll have a better picture of whether we can really have humans there and what that would look like. So I would say Mars is our best bet. There's people talk about other moons in our solar system, like Europa, for example, that could have evidence of people are looking for life because it's a very water-rich planet. So people are looking at that, but I'm mostly focused on Mars, to be honest, because I think it tells us the most about Earth, and I'm selfish as an Earthling.
Great. Actually, it looks like somebody either is passionate about or fearful of chemistry. I'm not sure which,
It's
but they're
usually
wondering.
both.
But they're wondering if there are areas of astrobiology or geobiology that don't need chemistry.
Totally. I mean, so chemistry is important to life. So if you're looking at a living thing, there's so many chemical reactions going on in my body right now. So chemistry is everywhere. So I will say that. But there aren't really going to be places when you do interdisciplinary science, like you're going to be bringing different things to the table. So if chemistry is not your strong suit and you like biology better, study biology, study those microbes. Tell us stuff that the chemists aren't going to know. So you can use the skills you have and the things that you have an affinity for. So things that you really like, that you look forward to in your school day, leverage those, work really hard on those, and you can absolutely contribute to it if you don't want to be doing chemistry every day, which is totally fair. But I also want to say that, you know, I failed chemistry exams before. I've had a hard time understanding concepts in chemistry, and in high school, truly it felt like I was really speaking like a different language whenever I did my homework or whenever I had a test. And as someone who does chemistry every day in the lab, I'm still looking things up. I'm not a chemistry expert by any means. And if someone asks me a chemistry question, I'm like, okay, I have a guess and I have like an informed guess about what the answer could be, but I still want to check too. I still want to make sure I'm getting the right information. So you don't have to be an expert in a subject like that. You don't have to be a chemistry genius or a math genius or a biology genius. You just have to be curious. And that's going to be the case no matter what field we talk about. So keep it up.
And it sounds like maybe a little bit of humility, knowing when you need to ask a question or bring in someone else who is expert.
Definitely. Don't ever be afraid to ask your colleagues. I mean, I ask my colleagues more questions than they would like all the time in the lab, and I'm constantly learning from them and from Professor Summons and my former teachers. So don't be afraid to ask those questions. You don't have to know all the answers. No one knows all the answers. So think about that next time you're in chemistry class and you're worried. Say like, okay, I'm just gonna do what I can to understand this, and I'm gonna remember that even the scientists are pretty unsure sometimes.
Mm-hmm. So I'm curious to know, if you could go to Mars, would you go, and where on Mars would you want to go?
That's a really good question, and I haven't really thought about it because I'm such a lab rat and I've been like stuck in lab on Earth, so I can't even imagine. But if I went to Mars, I would love to go probably to Jezero Crater just to see the mineralogy and all the different minerals in that ancient river delta and see what it looked like there. But I don't necessarily want to be an astronaut. I hear that's pretty intense training, and I'm really comfortable in the lab here and not having to worry about flying anywhere. So yeah, I guess if I had the chance to go to Mars and it was totally safe, I would explore the minerals and the rocks and look for methane, which is like a gas that could be produced by microbes or could be produced by non-living processes. But yeah, I'm pretty comfortable here, but I think that's a good question. And we are probably going to be looking for folks to go to Mars in the future. So if that's something you're interested in, keep your eye out.
I'm kind of curious how many people we have on today would go to Mars if they have the opportunity. Should we have people raise their hand?
Oh yeah, that would be fun. Okay, I see some raised hands. Two people so far.
Two?
All right, yeah. Good.
Nice.
All right, y'all are way more confident than me. I'm excited to see it. We're gonna keep
it
those
looks
hands.
Like maybe 1 out of 4, 1 out of 5 might be interested.
That is amazing. And when you have those instincts, you got to run with them. Keep going for it. As next time you're studying, your motivation can be that you want to go to Mars or other places.
Yeah, I think at this point we might want to just say, just get parental permission before you head out.
Yes, ask your parents. Do not go to Mars alone. Don't
Yeah,
don't
buddy
sneak.
system, definitely.
Yeah, don't sneak around in space.
Right. So we also have some questions about your work as a science communicator. So it
Good.
seems like you have this sort of two parts to the path of your career. One is as a researcher and really looking for early signs of life, but then again, also as a communicator. So do you want to talk a little bit about where that passion came from and what kinds of things you really like to talk about in terms of science?
For sure. So my journey through writing and communicating started when I was really, really young. For my grade 2 talent show in elementary school in the middle of the country, I wrote a play and casted my classmates in it and made them perform my play. And it was a mystery, by the way. It was very suspenseful. And I think my parents had encouraged me to write and to practice my English skills because English was not actually my first language. My first language was Urdu, which is a language we speak in Pakistan. So my parents took every opportunity they could to encourage me to practice my writing and speaking in English. So that was really crucial. But yeah, since that play, I've been writing pretty much nonstop. I've written a lot of short stories and poetry and that stuff. So getting into communication was pretty natural because the way I justified it in my head was I'm storytelling, and instead of making up things in my head to do science communication, now I'm storytelling about facts that are in front of me and telling stories in science. So it was a pretty natural transition. So if you're interested in writing or science communication, take a writing class in school or try to write about science in your English essays, or spend a little more time on that biology lab report where you have to write and explain what you did. That was really how I honed those skills and eventually worked for the school paper when I was in college, and I worked as a science editor and wrote articles every 2 weeks about whatever I was curious about. And then it led me to MIT, and now I can't leave.
Nice. So are you on your page on Global Campus? I know you shared some information about your work with Possibly, the
Yes.
podcast, the series. Is that still active? And I'm curious about where those questions come from. Maybe talk a little bit about what Possibly is, and then
Sure.
maybe we can have Rahi throw the link to it in there for folks that are interested.
Sure. So Possibly is indeed active. We just had an episode run yesterday on Rhode Island's NPR station. So it's a radio show that airs weekly and answers questions about sustainability and things that people could be doing to live more sustainably and to think about the environment and what you could do to just, have a good impact on the earth. So we answer simple questions that listeners from all over Rhode Island submit to us. So at the end of each episode, we're like, if you have questions, here's our website, ask us questions, and we'll answer your sustainability questions in 4 minutes or less. So as part of that, I help train the reporters who are Brown undergraduate students to answer those questions and how they can do interviews and become journalists. And sometimes I even interview people myself and help write episodes, and you'll hear my voice on air. You won't see my face because it's radio, but I'm there. So it's a really fun thing that I've been doing and hope to continue to do for a while.
And is there any one particular question that you really enjoyed exploring or putting together the piece for?
Right now it's actually an episode that hasn't come out yet, so I hope this still counts as an answer. Me and my co-producer, we were really curious about why we keep our eggs in the refrigerator when a lot of folks in Europe and other places in the world don't refrigerate their eggs. And we wanted to figure out, what is the environmental impact of this and why do we do what we do? And that's actually been so exciting to explore because I've gotten to talk to chicken experts, which I never would have dreamed of. I mean, again, I'm a geochemist and geobiologist. I don't talk to chicken experts as part of my job. So that's been really fun to explore. So that episode's going to come out in a couple of weeks. So stay tuned. And you can learn all about eggs and chickens and why we refrigerate our eggs and what we can do to be a little kinder to our environment.
Nice. So I did want to pause here momentarily and just let folks in our audience today know that they can raise their hand if they'd like to ask a question verbally. So when you do that, I can unmute you so you can so you'll be able to ask Fatima your own question. So there's a few folks who are interested in your writing career. So both like who was it that inspired you to write, and then are there particular writers that you follow? So both of those things.
Okay, so I mentioned in a previous answer that I started writing plays when I was really young. So as someone who was still learning the English language and getting a grasp on how best to communicate with other people, I picked up this like random book that just had a nice cover. And I was like, this is interesting and I'm going to read this book. And it turned out to be a collection of plays by George Bernard Shaw, who is a famous European playwright who writes comedies and dramas. So I think he's been the most influential writer to me. And whenever I am writing an email or trying to write an article, I'm like, how would George Bernard Shaw do this? And I really wish if I could travel back in time and meet anyone, it would be him. And who are people I follow today? I follow all of my colleagues who I graduated with from my writing program. So they're all young journalists, intrepid, finding the stories in everything. So I follow my colleagues, but I follow writers like David Quammen, who is a really fantastic nature writer, and Carl Zimmer, who writes the New York Times science pieces pretty often. I also love watching videos about science on the internet, and Science Girl is a really big influence for how we communicate in video. And she's actually, Diana, who is Science Girl, she's actually an MIT alum who studied physics, which is really exciting. So I get to learn about physics that way. And then I also just honestly, whenever I get a newspaper or get a chance to scan the web on my computer, I just go to the science section of whatever publication or newspaper I'm looking at, and I get to read those articles. And the best thing about it is you don't have to be a science person to read them. They're written for everyone. They're meant to be communicated with you, whether or not you know science. So there's no barriers there to actually accessing that, and it's really cool. And also, I love the National Geographic, because not only does it have amazing stories, it also has fantastic pictures. And I think that tells a lot about stories as well.
It looks like Hassini has a question. Would you like to ask it?
Who do you think inspired you the most, nature or humans?
Ooh, okay, that's a really, really good question. I would say probably nature, because I kind of consider humans a big part of that, but nature got me first. I think looking at the creepy crawlies in that plot of dirt I started out digging in when I was a little kid really made me realize that we're not the only things here. There are other things on this earth that live and breathe and play a big role in what makes Earth what it is. So nature is definitely the coolest. And actually my background here for this Zoom call is another shot of Iceland. It's actually it's where a lot of extremophiles would live. It's like a water source. I'm like leaning off the screen to show you my picture. But this is an environment where there's a lot of sulfur, which is an element that you may learn about in science class. And you and I, if we smelled sulfur like a rotten egg or something, we'd be like, oh, gross, I want to get away from that. I don't want to be near it. But in these kinds of environments, in Iceland and other places around the world, there are microbes that love it. And they love living there, and that's their whole life. And if you take that sulfur away from their environment, they won't be able to like it anymore. They're not going to be too happy. So I think nature inspired me because there are so many cool habitats around Earth and around our amazing planet that I'm like, oh my gosh, I definitely want to understand what's going on here a little bit better. So that was a good question. So definitely nature.
Well, I want to thank you so much for joining us today and sharing your work, Fatima, on exploring ancient life.
Thank you all for letting me share with you my background and what I study. So thank you so much, Carol, for organizing this.
No problem. Thanks for joining us. Thanks, everyone.